This meeting is now, there we go, we're finally recording. Batteries, last 3 examples of the semester, woo! All right. Real life applications. Batteries. You know, if I were doing this all online thing all the time, I could totally have like audio clips. I get a little Metallica playing right here. Yeah, awesome. Okay, but I'm not, and I don't plan to because I don't want to because it sucks. I miss seeing you guys. Must be the coffee. I'm getting emotional. The lead acid battery. This is what is in your car. The lead acid battery is 6 2-volt batteries in series to make 12 volts. Have we been doing anode and green, cathode and red? Does anyone remember? Of course, I'm glad I chose those because that means any red-green colorblind person is, it's all lost on them.
Anode is green.
All right, now you guys are gonna make me look. Say again?
You're correct.
Okay, anode is green, cathode is in red. Oops. So the anode looks like this. You have lead plus hydrogen sulfate goes to make lead sulfate, lead 2 sulfate if you want to get down to it, plus a hydrogen plus 2 electrons. The cathode looks like some lead 4 oxide, so some PbO2, plus hydrogen sulfate, plus 3 hydrogens, plus 2 electrons, goes to make lead 2 sulfate and 2 waters. At the end of this, you add these up, you get the solid lead plus lead 4 oxide plus 2 HSO4 minuses plus 2 H pluses goes to make 2 lead 2 sulfates and 2 waters. To be noted, if I took those 2 things and put them together, what does that look like?
H2SO4?
That is correct. Okay. So given that these are the reactions, hopefully you guys can see why this is called a lead acid battery. We have lead, we have acid. Now, this is the other really cool thing about lead acid batteries. Let's go ahead and build it. Draw myself a nice little H cell here. I'll go ahead and put my anode, I guess, on the left, even though it's on the right in my other one. My cathode on the right. Okay. Now, if we go back up to the anode, Alexia, what do we need to make this side of the cell? What are our ingredients?
Lead and H2SO4 and PbSO4 and H plus.
Yes. Let me modify that because I thought you were actually making a leap ahead and you almost did. I'll do the HSO4 minus and the H plus, and then you said the PbSO4. Okay. Oops. I want to point out that you had it. I just thought you were making that last little thing to say HSO4 and H plus is really our H2SO4. So our sulfuric acid will actually supply both of those, right? It's a strong acid. It likes to give us all of its H pluses. We all know that it's really the first H plus that is dominating everything. So this will be an equilibrium of H pluses and HSO4 minuses. Of course, there'll be some sulfates floating around there too, but very little because of the Ka, specifically Ka2. Okay, on the cathode side, let's go with Celeste Main. What's on the cathode side? Or Rio? Or Soto? Who am I kidding? Let's go back to Dallas. He'll talk to me.
Okay, so that should just be the PbSO4, right?
Well, you do need that. That is correct. But you also need.
Is it water?
Sure, but this is an aqueous environment. You need the PbO2. You need the HSO4 minus, and you also need the H plus, which, as you pointed out, this is also H2SO4. Okay. So on the anode side, what will our electrode be?
Lead?
Yep. Now on the right, it's not going to be intuitive just yet. Hey, is Ben in the house?
Yeah, I'm here.
Cool. What do you think we should use as the other electrode on the cathode side?
Carbon or platinum?
Close. You're one letter off. We're going to use lead. And you'll understand why in just a second. Okay. So back to the left-hand side. We've clearly said that we can get away with 1 molar H2SO4 to get us our 2 ions. And then we need to get ourselves some PbSO4. So how should we do that? Well, we could probably get away with bearding it. So I'm going to choose, do I have another color I can use? Let's see, I'll use this rusty color. So I'm going to do
I have
this.
a quick question. How are we getting our ingredients for the anodes and cathodes? Are we just looking at each one separately?
Go ahead. You're looking at that reaction.
Are we looking at each one separately or after we add them together?
Separately, because we have them on separate sides.
Okay.
Okay, so this right here is bearded PbSO4. So we'll get that thing in there. We'll put a charge on it. Bam. We're going to beard. Now, I've only bearded half of it, and you're going to see why in just a second. On the other side, we need that PbSO4. So let's go ahead and beard that. But we also need some lead oxide. And that one I'm going to choose to be, I don't know, gray. So we're going to go ahead and beard that. Oops, PbO2. And then, of course, we need the 1 molar H2SO4 as our electrolyte. Now, I'm going to do something. Hear me now and believe me later. I'm going to go ahead, oops, and I'm going to put some PbO2 over here. Now, here's the reason why. First, let's ignore the PbO2 on the left-hand side, and let's talk about, well, let me just take it off first real quick. Actually, maybe I shouldn't have put that on there just yet. But you guys can leave it on your notes, but just walk with me for a second. So here's the deal. You take a lead acid battery, and you get all your ingredients for the anode and cathode. That is the reaction. These are the reactions that occur for this. You will make some lead oxide and some lead sulfate, and that lead oxide will turn into lead sulfate and vice versa. So what happens here? On the anode side, basically the lead sees the HSO4, becomes lead sulfate, hydrogen ions, and spits off those electrons. They come over here and hit the cathode. Those electrons and some H's floating around come up there with some sulfates. Bam! Blow apart the lead oxide layer, convert it, blow apart the lead oxide layer, convert it into a lead sulfate layer, and spit off some waters. Now, there's a fun thing about this. First, I want to do the cell diagram and then show you why I decided to beard the other side with something that appears to not need to be there, and that is that lead oxide. So let's do the cell diagram here. We're going to run our way to there. The cell diagram would look like starting with a PB. The next thing I would see is my PbSO4. The next thing I would see is 1 molar H2SO4. The next thing I would see is my PbO2 and my PbSO4 layer. And then finally, that lead again. Now, 2 things to note about this. What's weird about this cell diagram?
There's
There's no middle thing.
There's no middle thing.
Isn't it because it's the same
Dallas, you
thing?
guys were right. Say it again.
Isn't it because it's the same thing?
It is the same thing. Now this is
thing.
you don't need one. And this is the fun part. And this is what makes car batteries, these lead acid batteries, so awesome and so ubiquitous around the world as one of the battery sources that we have. Membranes slow things down. Membranes get clogged up. Had we been able to do lab, you would have seen that some of your electrochemical cells would have been slightly discolored along that little membrane in between. And that's because over time, stuff just gets stuck. And so over time, any of your batteries that have some sort of membrane to keep them separated, they'll basically die by a million different ways. And one of them happens to be your membrane just gets clogged. Membranes also slow down the flow of the ions. Think of, whether you can swim freely from one side to the other, or do you have to like hit there and go through a bunch of channels because you're trying to keep someone else from coming the other direction. So that right there speeds up the transference of the current, right? The flow of those ions. Now, Ben or Tristan, because I think you two are the ones with the most experience on this. Why did I want to put this guy, this PbO2, on this side? Can you think of why I wanted to put that lead 4 oxide on the anode side, even though it's not in our anode equation?
So that way either one could be treated as an anode.
That is correct. And that also means that anyone could be treated as the cathode. Now, there's a nice little piece of equipment on your car engine that likes to run every time you do any sort of errand. You start up your car, you go. Has anyone ever thought why their battery doesn't just die? Ben, Tristan, say the word alternator.
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 No. What does the alternator do in a car?
Alternates.
Yes, it does. So Dallas, since you're going to go ahead and at least speculate here, what do you mean by alternate? What is that alternator doing?
Well, if I had to guess, given that we just started talking about how either side can be treated as an anode or a cathode, I'm going to say that it switches which one is the anode and which one's the cathode.
That is absolutely correct. Now, this is the whole deal about your alternator. If you did not have that alternator in your car, and most of your small engines that you have for like riding mowers and stuff like that, they don't have alternators in their engines. Those batteries don't last very long because those batteries are one-way trips. The alternator in your car, every other little stroke of taking a spark or not, pushes electricity back into your battery to try to force everyone to go the opposite direction, shoving it out of the equilibrium so they can draw that energy back. It basically, for every spark you take to ignite your gasoline, the movement of the engine and the mechanical of that makes the alternators inductors shove energy right back to the battery to try to keep it charged. Now, it's not a zero-sum game, right? Mother Nature is going to take her tax. It'll come out in the form of heat or other inefficiencies, and your battery does go down. It will die, but it's going to take it a lot longer because the battery is going to be switching it back and forth. And the nice thing is, again, we don't need a membrane here, so we can actually get away with some very fancy things. Now, I went ahead because I care, and I looked up one of these here. Move that out of the way. That's not what I wanted, the lead acid battery. So the lead acid battery, you can have your anode and your cathode. They're completely separated. And with this water aspect, this is something that if you talk to your parents or definitely your grandparents, one of the things that was interesting about lead acid batteries is up until maybe, 20 years ago or so, there were 6 little caps on the top of a battery. And let me see if I can actually get a picture of a battery here. Move that away. Oh man, everything's in my way. So just wanted to sort of show you this.
Is each one of them supposed to be one of the 2-volt batteries?
Yes. I don't know why they typed it in there. See if no, that's not what I wanted. I wanted an image of it. Predict me better. So yeah, you see these little knobs right up here? Get over here. I didn't mean to do this. Okay. That's a new battery. You see these little 6 screw holes up here?
Yep.
Yeah. So those used to look like, let's see, used to look like little knobs like this on top. In old batteries, because that water is being produced on the back end of this reaction, and because those batteries are getting nice and hot, essentially the water would slowly evaporate out of the battery. And one of the things that had to happen is if your battery was starting to go dead a little bit, you would actually pop the caps off of there and pour some more water back into the battery to give it a little bit of extra life. Nowadays, they pretty much seal them up so that unless you really know what you're doing, you're not going to be able to get in there and do it. And for the most part, they've sealed these up well enough that the water really doesn't escape. So the water usually isn't your problem. Here's your problem. So let's go back to this guy. Okay, so if you are charging, you notice that what's happening on the electrodes here switches between discharging and charging. The reactions go back and forth. That means that the ions that flow have to flow one direction and then the other, and one direction and then the other. And in every situation of our reaction, we are taking off and redepositing and taking off and redepositing these solids. Okay? Now here's the thing. Do you think they go back where they should? The answer to that is no. This here is a picture of a brand new battery, what it would look like on the inside. You can see the plates of lead, and you can see the 1, 2, 3. In this case, I think there should be a 6th one here. This one may only have 4 for some reason. But these are the individual 2-volt cell configurations. You run them all together, you get 12 volts at the end. Every time you cycle it forward and backward and forward and backward, that solid is broken apart and then redeposited and broken apart and redeposited. It does not go back where it should. And this is what ends up happening, is those solids basically follow the path of least resistance. And so if there is even 1 molecule's worth of difference of distance to the plate that it needs to go to, it's going to start sticking there, which means essentially these plates slowly but surely start to grow together until they finally touch. And when they finally touch, that's a short circuit, and that cell is now dead. And the battery now won't give you 12 volts. It'll only give you 10.
So it favors places there's already deposits?
Well, if you think about, I mean, yes, the answer is yes. And that, just trying to think of a circumstance that would relate to you, Dallas. And I can't, because it all involves heavy physical labor like I do around here, and I doubt you've done like I did this weekend, and I moved a wood pile.
I've moved wood piles before.
Okay, okay, if you've moved wood piles, Dallas, then you can think about moving a wood pile. If you are trying to stack wood, the proper way is to pick up that wood from one place, go to the other place, put it exactly where it needs to be. But if you're in a hurry, or you're lazy, or you're tired, you're just wanting to move that wood from one place to another, not necessarily stack it nice and neat and perfect. You're going to put it down at the first place you can find. And that's usually the closest distance you can get. I mean, it's touching the rest of the wood, right? So it's technically part of the wood pile. And you'll shorten the distance you have to walk to pick it up and place it somewhere else. And that's what these ions are doing. They're going from one plate to the other. Now you can imagine, hopefully, if you guys can sort of see this, that if I start to make a little bump right here, I've just shortened the distance for this ion to travel backward. And so it's going to follow the path of least resistance, and that is the shortest distance. And so as long as it's touching, making it solid, it doesn't care. Why go here and go like, oh, there's a bump. Let me go down here and just be, nice and flat. No, I'm just going to go as fast as I can. You told me to go fast and give you my power. I'm going to do that. If it means that I end up looking like a damaged battery like this, well, then so be it. You're the one that made me work that hard. Actually, you guys can probably see the water caps on these old batteries too.
Yeah.
If you go back to that battery diagram that you were just on, how come they use over on the right, it says that their cathode is PbO2?
No, it actually is a lead. There's see that this is one reason why I thought, hey, I'll show you guys some more professional drawings, and then I looked at this and I was like, they're not going to notice that each of these is a hunk of lead.
Oh, okay.
They need some sort of piece to be the metal. You notice that over here that you can definitely see the solid lead. They should have had the solid lead over here when they were going the other way. So basically they weren't as thorough as I would like them to have been, and they didn't have all the pieces that should have been there. You'll have lead on both of them because at any given time, one of them is going to be this anode that needs that solid lead proper.
Yeah.
And since you need the solid lead proper, just use it as the electrode. It conducts electricity. Everyone's happy.
So then for your cell diagram, do you not have to note the PbO2 that you put on the
So that's in the one way, right? So let me be clear. You're right. So this would be discharging,
Oh, okay.
right? And charging would be exactly the opposite way. PB with PbO2 and PbSO4. 1 molar H2SO4, PbSO4, and then finally Pb. This would be if you're charging.
Scio10 would like you to scroll back up a little after this.
How far? I assume that's enough.
Yeah.
Oh, that is okay. Good. So this is one of those situations where we can sort of see a real life application to this whole mystical, magical. Okay, I get it. We can do some work. Well, these are the ways we do work, and we can throw those electrons through devices, and we can power them. And lead acid batteries are really just one of the big workhorses here. They run for a long, long time. Lead is cheap. Sulfuric acid is cheap. So that's why we use them. Are we done, Tanaris?
Actually, I have a question about the lead acid batteries.
Yeah.
And so when we talked about how you beard stuff, you were saying, okay, you put the thing in and then you apply the voltage and, it'll cause it to bond and stick to it.
Yep.
So when you put the lead in there and apply the voltage, will it form both beards?
No. Good question. So a common way for them to do it is exactly how I showed it. You notice that I've coated half. So to prepare these, oftentimes they'll dip half of it into the solution, go zap, dip the other half into the other solution, go zap, and they will form it on both sides. Because it doesn't matter where it is, as long as it's there, you can have it. But once you beard one, you probably can't beard the other one on top of it because it's a different reaction. So you can just stick in little pieces. If you really wanted to get fancy, you could actually do some sort of, for lack of a better term, lithographic nature to it. And that is where you could actually cover up different portions of that electrode, electroplate, take off that covering, cover up the other part, and electroplate the parts that you had originally covered up. As if you want to get fancy. I've seen some of my friends in grad school, and they were electroplating stuff. They were screwing around and making patterns just by covering up things that they didn't want to be plated. So they would like electroplate their name on something, and good on them, I guess. Tanaris, can I move forward? And he says,
Yes.
yes. All right.
By Cyoten.
That's Tanaris, by the way, Dallas. Cyoten is his avatar something name or whatever, his alter ego, crime fighting ego. All right. One down, here we
Alias,
go.
I think, is the word you're looking for.
Alias is correct, but I was looking for some sort of idiom, sir? Yes, that's the name. Nickel, cadmium, also called the NiCad batteries. These were one of the first commercially available, where you and I could go pick out a rechargeable battery. When I was a kid, these things came out, and they were the bee's knees. They were awesome. You could drain this battery, you could hook it back up to a power source, and you could recharge it back up, and it was great. We take rechargeable batteries for granted now, but 30 years ago, 40 years, 40 years ago, these were all the new hotness. They were also not the easiest thing to work with, because while we have battery chargers and everything, where if you plug it in and you're charging and it's done, it stops. They didn't have that back then. So you actually had to monitor your battery to make sure that you didn't overcharge it, because you would basically make it explode. You'd build up so much heat that you would make it explode. And I did that once as a kid. I didn't know, and then my grandfather had to tell me, how to charge it up right. There weren't regulators on it and everything. They expected you to monitor your stuff. Then they find out that human beings don't do that, and figured out a way to monitor the charging and turn it off when it's done.
They probably knew how to do that to begin with, and they just sold the alpha version that didn't have it, so that way they could sell the safety feature later.
Well, they took a long time to sell a safety feature if they did. I'll tell you that. All right, so this is how this looks. It looks like nickel oxy hydroxide. That's kind of a weird looking way of writing it. Plus cadmium. Goes to make cadmium hydroxide. Plus nickel hydroxide, specifically nickel 2 hydroxide. Now we actually write the OH in parentheses because it is called nickel oxy hydroxide. I don't want you to think that's some sort of weird carboxylic acid group or something, but that is how that is written. If we break this apart into its two constituents, let's see, oxidation is lost, we did that. So that's the anode. We have cadmium going to become cadmium 2 plus 2 electrons. And if we do the nickel oxy hydroxide, you end up with an electron plus a water plus nickel oxy hydroxide, going to make nickel hydroxide and some other hydroxides. Now, of course, we're going to have to multiply this by 2. And this is where it gets kind of fun.
How come you don't include the hydroxide in the cadmium one?
Oh, you're going to see that right now. This is where it gets kind of fun. And this is where, when we get to the end here, result, you'll see that this ends up being cadmium plus new 2 nickel oxy hydroxides plus 2 waters goes to make 2 nickel hydroxides. And here's the fun part. That technically becomes your cadmium hydroxide. And you'll see why that's an interesting little guy right there. Because what we're asking is that cadmium to spit off its electron. Well, it will, and then as soon as it sees the hydroxide from the nickel side, it will become the cadmium hydroxide. So that's the sort of end result of it, but we needed the cadmium to turn into its ion first, not just an insoluble compound. And so this is another cool little guy here. If we build its cell, okay, now we've just sort of been doing this as the anode and the cathode, even though it's actually backward in my notes. I can roll with it. On the anode side, it looks like we need cadmium, and as has been pointed out, the cadmium hydroxide. So we can use our anode to be cadmium, and we can go ahead and put some cadmium hydroxide. Now, on the other side, we don't have solid nickel, do we?
What?
We don't have any solid nickel, do we?
Technically, no.
No. And this is the other reason why it took so long for these guys to pan out. Because if you don't have that metal, you have to use something else. And in this case,
Platinum.
yeah, it took a while for these to get commercially available, because one of the reasons why is platinum was very hard to find and get out of the ground and do their stuff with, and it was expensive. Now, on that electrode, oh, I forgot to do my cool little watery things. On that electrode, you would need to put beard on one side and beard on the other. Let's do, I don't know, this color. Here you would have your,
That is two very hard to distinguish colors.
fair enough. I will give you dark green. So this one might be your nickel oxy hydroxide layer, and this one would be your nickel hydroxide layer. Again, just put it on there. Now we do need an electrolyte to transfer this stuff. We need some charged stuff in there. What do you think we're going to put as our electrolyte?
What's an electrolyte?
Like KOH or something?
KOH or more easily, sodium hydroxide.
Oh.
Right? KOH is fine too. Either one would work. Now, this is the fun part about this guy too. Did you notice something else about this cell?
it doesn't have a membrane either?
It also doesn't have a membrane. And that was one of the other key things to this, is that they didn't have to put a membrane in this. You essentially could take these two metals, cadmium and platinum, and just sandwich this really pasty substance that contained a whole bunch of sodium hydroxide in it and roll them up. You didn't have to have some very special membrane to make sure that one ion didn't get to the other side because it would poison that cathode or anode. They could just freely go forward and backward. This is why it was so cool, because all you had to do was pump the current the other way and you would recharge the battery. So again, you didn't need the membrane. Everything flowed faster. It was pretty cool. So again, we have cadmium to the cadmium hydroxide to the 1 molar NaOH to the nickel oxy hydroxide to the nickel hydroxide to platinum. Now we have the lithium polymer batteries and such, and those have their own diagrams, and depending on the type of lithium ion battery you have, whether it's a lithium cobalt, a lithium polymer, all of them in general are called lithium ions in general, but they all have different, slightly different mechanisms for how they work. So I'm not going to go through and do one of those, because there are so many varied ways of making a quote lithium ion battery.
So why did we use the 1 molar NaOH as the electrolyte again?
Because take a look at all those OHs that everyone has,
Oh, okay.
right? It's in a base. This is one of those ones where I said, hey, remember, we're going to balance in an acid, balance in an acid, balance in an acid, and most of them are going to be an acid, except this very beautiful example of where the basic solution was what we needed. And a strong base like sodium or potassium hydroxide will definitely be a good electrolyte to transport that charge. And so because it's in a base, we're going to use sodium hydroxide.
Okay.
So you mentioned how since we don't have any solid nickel, we can't use nickel as the thing.
Right?
Why not? Like if you did try to build this and then just put nickel instead of platinum, what's going to go wrong?
I could only conjecture, but I would imagine that when those electrons decided to well, I mean, actually, if you put the nickel in a basic solution proper, basically it would just make nickel hydroxide on the surface in general. So you would be essentially poison your surface with only the nickel hydroxide, and that would just occur whether or not you had current flowing. And so basically, as it sort of sat there, any of that nickel that could see any hydroxide would slowly just poison itself to the point that you wouldn't have any of the other piece, and it just wouldn't work. I'm sure they probably said, hey, can we get away with this? And they did it, and they're like, nope. But that's just my conjecturing at the moment. I don't actually have a full answer for you.
All right.
But my suspicion is that nickel hydroxide would just start forming whether or not you were using the battery, and it would just slowly poison the cathode there. All right. Last one, and then you guys can go do whatever you do. The fuel cell. Hydrogen, a couple hydrogens, plus an oxygen. Goes to make a couple of waters. As we look at this, we have hydrogen going to make hydrogen ions and a couple of electrons. On the other side, we have oxygen plus 4 hydrogens. Oops, I need to move that over. Plus 4 electrons goes to make 2 H2Os. Of course, you're probably noticing that I have to multiply this by 2 to get everything to work. And at the end, we get 2 hydrogens plus an oxygen going to make 2 H2Os. 4 electrons are transferred. Oh, I meant to show you guys. Oh, I meant to show you guys the cadmium one. That one actually wasn't that exciting, so I'm not going to show it to you, unless on accident. There is actually another version of the fuel cell out there that talks about hydroxides being formed. I'm going to talk about the H's being formed. If you look at this, it looks something like so. This cell is going to look different than the others. So I'm going to draw a little chamber here. It's going to look something like this. It's almost an H that I put down on the side, but I want to put this here. So okay. So what I have here is some good old-fashioned platinum. Now, hopefully you guys can already see the reason why I'm using platinum. We have no metals as our electrodes. On one side, you're going to flow in some hydrogen gas. The hydrogen gas is going to come down in here, and it's going to spit off H pluses, while the electrons get spit out the top through our wire. On the other side, you're going to have oxygen gas being flowed in. That oxygen is going to come down here, and it's going to see these H pluses. So these H pluses are going to keep coming, and they're going to hit this side, and H plus the O2s make some good old-fashioned H2O. And that's going to happen because here come the electrons. So here we see the electrons and the H's will see the oxygen gas. They'll transfer their electrons to it, rebond, and form the water. This guy right here in the middle, this guy right here is a polymer electrolyte membrane. And basically, it's just there to let the hydrogens get across in a watery environment so they can see the other platinum. Now, technically, you don't actually even need the membrane. You could just put these two in a watery solution because hydrogen ions do flow through water. The membrane just helps separate the two electrodes because you have gases flowing in. But you could try to do this if you wanted by just merely bubbling some oxygen basically on one side and bubbling some hydrogen on the other, and just make sure the electrodes are far enough apart that no oxygen gets over here, no hydrogen gets to there, and it could flow without any membrane. No, I already told you that last time. Isa, come on. Isa says, do we have to do this on the exam? I'm loosely translating. I'm just kidding. No, I said today was just about giving you the applications. There's no way I would expect you guys to know how to build these types of things. These are very specific examples. No, in general, you'll have an electrochemical cell, and I'll talk about that at the end of this lecture, that you'd have to do. I mean, let's face it, I'm sitting here staring at my notes to try to make sure that I remember all the ins and outs of this reaction. So I would not expect you to do this. I just want you to note that this is how it works in the real world. And again, you could flow if you really wanted to. I mean, this is just for kicks. I mean, let's face it, you could have some sort of situation like this where you just have a salt bridge, a little watery bridge. Oops, wow, that's an MC Escher thing right there. And you could bubble up O2 on this side to platinum mesh, and you could bubble up hydrogen on this side to platinum mesh, and just let them go at it, because the only thing you have to do is make sure that this oxygen gas does not see this guy, and the hydrogen gas doesn't see this guy, and it will just work. That was one of the nice things about fuel cells when they came along, when we finally figured it out, is as long as we don't let the oxygen see the hydrogen electrode and the hydrogen see the oxygen electrode, you can get away with just leaving it in a watery mess. The problem is controlling gases, which is why they developed this membrane, so they could flow oxygen right next to this platinum and let it go by. The hydrogen would go by, and if you're wondering what the exit stream here is, this is excess hydrogen. Any hydrogen that didn't make it can go out the other way and get recycled. Now, it turns out they use platinum because platinum is a catalyst to this. Yeah, it's okay, Isa. I'm sorry. I didn't mean to make too much fun. I apologize. That seemed kind of harsh when I was making fun. So I apologize for that. But no, this is all just for edification, Isa. Platinum has this unique ability. If you guys remember back to the catalyst example that I did in class, where I said it is still kind of unknown, but that platinum actually weakens that hydrogen to hydrogen bond and allows them to break apart a little bit more. And in that example, I even just showed the oxygen swooping down. That essentially was an electrochemical cell. The only difference was we weren't separating them to get the work out. We were just going ahead and saying, look, if I put the platinum down and those hydrogens separate out, then the oxygen can come down and actually just take it out. I think, oops, wrong thing. I want to see if I can get this, and then I can like delete it. I just hit the backspace and get rid of it. Nice. You guys might remember I had that thing where I had the platinum, and I said I had my hydrogen coming down, and those hydrogens, that bond would weaken, and then the oxygen could come down, swoop, and bam, on the back end we had H2O. That was, for lack of a better term, an electrochemical cell, or at least an electrochemical redox reaction. We just didn't separate them to get the energy through it. So that's one of the reasons why they use platinum. And again, one of the reasons why fuel cells are still expensive is we only got platinum. The nice thing about this platinum versus other platinums, so we use platinum in catalytic converters in cars. The platinum in your catalytic converter can eventually start fouling up because it's not complete combustion and you are shoving a bunch of soot and stuff over that electrode. It eventually gets dirty and it fouls up. And so sometimes you have to replace your catalytic converter, especially if you have a very poor burning engine. There ain't no carbon in this. There's nothing to clog it. There's nothing to make it dirty. It's beautiful. As long as you have good, clean water to keep everything moist here, you don't have like crazy stuff. What do you got? You got two gases. There's nothing to foul up this membrane.
So when you say that platinum stuff, that's supposed to be a platinum mesh, right? Just because a solid hunk of platinum wouldn't let any gas through, right?
Oh, Dallas. Your homework is to go look up solid oxide fuel cells. That one will blow your mind. So yeah, for every absolute, it always seems like we find it an exception. There actually are solid oxides where you actually will not have to have this flowing aspect, and you can actually just have a solid surface, and it's kind of cool. I'm not going to go into it, but I know your inquisitive mind is probably already Googling it, so you can look it up and then start asking me questions about it, and I'm going to sign off before you can. So that's the end of it. That's it. We're done. Oh wait, I did want to show you though, because I did pull up one of those. Where's my fuel cell? Get out of my way list. Schematic. That was the cadmium one. Where is? No, I thought I had my fuel cell up here. Oh, there it is. So again, this is where they have this electrolyte. They put all their electrons on the bottom and everything. And this is a nice cleaner version of what I put up there. But again, since the hydrogens have to go one way, all we're doing is making sure the gases can't see each other. So they put this polymer electrolyte membrane just to keep them separated out. But this is a little bit more about what it might look like in a real life diagram, or at least pictorial diagram, if you will. All right. So I guess that's it. Isa, ask your questions before I stop recording. In the shortest lecture ever.
I don't think I have any at the moment.
Oh man, somebody's got a question. Any question?
I've got a question real quick.
4 hours. That's how many hours I slept last night.
Could you scroll up to the nickel cadmium example?
No.
No.
Closest. No, I'm kidding. I will. What did it say? All right. Of course, Tanaris wanted to say what's on the exam. All right. First, let's go up to this one. What do you have, Tristan?
So over on the anode side, right, we say that we have CdOH2. Where do we know to pull that from? Because when you look at the anode equation, right, it's just Cd goes to Cd2
Right.
plus.
And so this is, yeah, that was sort of asked earlier. It's like, where's my cadmium hydroxide? You need the electrons to pop off. And if your cadmium just went to cadmium hydroxide, you would say like, oh, I guess, let me see if this helps. So we have cadmium going to cadmium hydroxide, right? So if we look at that, we would add a couple of waters over here. We already have we have 4 hydrogens and everything like that. Here's where it gets messy, right? And the reason why I didn't put it as cadmium hydroxide. So right now I've accounted for all of my hydrogens, right? All 4 of my hydrogens, both of my oxygens, all of my cadmiums. And then the last step is to say, balance your charges.
Yeah.
You see?
Yeah.
There's no charges to balance. And you'd say like, oh, well, there's nothing that happens there. Well, clearly something had to have happened in order to do this. And so what we're saying is you can't just go there, because you won't be able to see the fact that the cadmium spits off the 2 electrons, becomes positively charged, and as soon as it does, it sees the hydroxide from the solution, and bam, there it is. Bam, there it is. We just aren't going to put it there, because otherwise you wouldn't be able to see the electrons getting spit off where these guys could take them.
Got it.
And so that's why, yeah, I know it was kind of a sleight of hand I did on you there, but it was necessary, because otherwise you'd be like, well, I balanced it, there's nothing happening. Okay, so the answer to you, Lion Lee, is 42. Are the post-lab questions required to be turned in for lab 8 and 9? Is it required to turn in the lab report and post-labs for 5? Lua. Yes, and yes. Hold on, Dallas. I gotta get Tanaris first. He said, what's on the exam? Oh, man. For once, I'm actually okay with that. All right, we've been doing a lot. And since this is a weird section where I haven't seen you guys for the entirety of this section, let's take a look. I'm going to close down the chat thing so I have some more room. I'm going to close down my participant list so I can see a little bit more. All right. We started out here with what? Thermo, right? So if we look at thermo, we need to know that we got the delta G is delta H minus T delta S. And what kinds of things did we do from that? Actually, let's get rid of the thermo. Let's do more thermo. Clearly, you're going to have something about you got some stuff. One's hot, one's cold. And what do you do with that? What's their final temperature? Or I can make you solve for somebody's heat capacity. Or I could have you solve for an amount of stuff that got tossed in based on the rest of the data. What I mean by this is at the end of the day for these types of problems, you have what's going in and what's coming out, as it were, you know, heat loss and heat gain. You're just going to solve for one of the variables. You have one equation, you'll solve for one unknown.
Okay, question.
Yes?
When do you know when to implement the fusion? When heat is released? Because there's some problems on the homework where heat isn't released, where something is, let's say ice is completely melted and you don't really implement fusion. Then suddenly,
Well, if ice is melting, you have to do the fusion.
okay.
Question.
I
Did I or did I not give you guys a fun homework for thermo stuff? I can't remember.
No,
I do not recall such a thing.
Nor do I.
Huh.
you asked me to
Well,
email you, so I emailed you twice, but you didn't. Still.
Oh yeah, chef. Yeah, throw me under the bus there. Oh wait, it is my bus. Hold on. I could have sworn. I'm gonna look again because I could have sworn that I did eventually find it, chef. So I'm gonna look again because I would have probably put it on my USB stick, but I don't want to waste time. If I can find, by the way, guys, if I can find this old take-home quiz that I gave years ago that I was really happy about, I'm going to give it to you guys. And it's way harder than anything I would give to you. But if you can work your way through these problems, you'll do just fine with these type of thermal problems.
Will you give the answers to the practice quiz?
Do I have the answers? I'd have to redo them, and then yes, I could get you the answer to that.
Thank you.
Yeah. Oh, look at me making more work for myself. Yay. Okay, so you're going to definitely have something like this where it's going to be some sort of combination of something heating up and something cooling down. You'll solve for one of the variables somewhere in there. Okay, enthalpy of reaction. At the end of the day, this was products minus reactants, right? You can figure out how much it is. And you can figure out if you have a reaction, you can get the formation of one of the guys. If you have all the formations, you can get the reaction. That's pretty straightforward. Gibbs was exactly the same thing, products and reactants. You want to be able to identify whether or not it's going to be spontaneous or not. And what that sort of means. I would have to give you this kind of data. You'll want to be able to know that you can get the KSP from Gibbs. So if I give you a bunch of data for H's and S's, you can pull out your Gibbs. You can give me a KSP. And then it's just been electrochem, which is can we balance the equations in the acids and the bases? Can we add them up? If you're given the information for an electrochemical cell, can you make one? Specifically, you know, if I were to give you a question that says like, hey, if you have this reaction right here, this mercury iodide, okay, you need to be able to break it apart yourselves into the oxidation and reduction. So you got to remember that you got to break it apart with electrons. And you got to have the metal doing its thing to give you those electrons back. and then you can build one of these guys. And of course, if you build it, guess what you can get? The KSP. So you can see how these problems can sort of build on top of each other. And the batteries, of course, is not going to be on here, Isa. These were just for fun.
Thank you.
So Tenoris, did that, and the rest of you, did that sort of, highlight the kinds of questions I could ask you?
Yes.
Okay. So, you'll definitely be building a cell. You'll definitely be doing some sort of, heat in equals heat out. You'll definitely be solving some sort of delta H of the reactions overall or a portion thereof. What's one of the pieces inside and things like that. And there might be some conceptual questions about thermo too. Like I said, I haven't completely made it, but those are the types of questions that I could start asking you guys.
So regarding the labs,
Yeah.
I've been trying to do lab 9
Why don't we
for a while
meet,
now.
Why don't we meet after the lecture and I can help you out?
Sure.
And I also have a question or two about the homework.
No questions for Kyra. No, come on, Kyra. We'll meet after the lecture. I just wanted to get any major questions, blanket questions before I stop the recording.
Okay.
Hey, when's our exam?
This Thursday, and then the finals next Thursday.
Oh, perfect. I got a day to write your exam and make sure it works right. It will be just like last time. You guys will download it, work it, and upload it again. Has anybody been having a problem with that?
You mean besides the fact that my internet just doesn't work sometimes?
I agree. It just doesn't work sometimes for me too. I'll give you guys a big enough window for it.
Yeah, because it's sometimes stressful, like if you're trying to submit the exam
Yeah.
and then like your internet decides to crap out on you and you can't do that. So like a little bit extra time would be great.
Oh yeah, no, I'll get you guys solid on that. I mean, as Meng can attest, she's here, right?
Yeah.
Okay. Oh, there you are. Yesterday was a nice little poop storm with my Chem 110. I got booted out 3 times, and I had about 15 minutes of dead space. So dead that I actually ended up trying to make Meng my phantom hand and continue the lecture with me talking to her over the phone so that she could write it down on the screen for the students to keep going. And then my internet came back and we were able to go run with it. But yeah, no, I get it. People's internet comes and goes. I mean, even if you have Comcast, I'm sure sometimes it comes and goes because there's so many people streaming Walking Dead and well, I guess that's the new hotness. I don't know. What's the new hotness? The Witcher? I don't know. I'm trying to stay up on pop culture and I just can't. That's why I'm just slowly sliding away. Any other questions? Oh, there's another thing in chat. Why are people chatting me? Oh, Lion Lead says just me. Oh yeah, no. Yeah. Anything else? Kyra?
Louis Miyazaki asks what the first thing Jeffrey Dahmer said when he got to prison was.
What's the first thing? I don't know. What?
Don't mess with me. I eat guys like you for breakfast.
Oh, too soon. Of course, half this class is going, who's Jeffrey Dahmer?
No, there's
Guy
nothing special on him.
who he was a cannibal is the important part of that joke.
Oh, thank you for explaining it to me, Dallas.
Well, you were just going to leave everyone else hanging.
What time are you gonna try and pop in office hours today?
Actually, I was gonna close this out and do some office hours right now.
Okay.
until lunchtime. And then I have a 12:30 department meeting, and I don't know because I haven't been able to check my email, but I either have a 2 or a 3 o'clock meeting with union stuff. So basically, hopefully I'll get you guys all dialed in the next hour. If not, I'll try to come back at late afternoon. And like I said, I don't know if my meeting is at 2 or 3 today. And that'll dictate probably when we get on the back end. Since it's negotiating, it'll either be very easy or it'll be a long slog.
Okay, cool.
So again, right after now and then late this afternoon.
Cool.
Okay, I'm stopping this meeting. Ready? Stop recording.